Okay, so chapter 10 is all about logarithmic and exponential equations and functions. You've probably seen them before when you've talked about like interest in your bank account or something like that. You might have seen them sometimes in science when maybe you're talking about bacteria in a petri dish, right? Or something like that in biology when all of a sudden it goes along and then whoosh, I have a whole bunch growing in my petri dish. Things that we might see with this sort of stuff are like populations of bunny rabbits. You know, all of a sudden you got one bunny rabbit in your neighborhood and then they go and have 42 babies and then you've got 8 million bunny rabbits everywhere in your neighborhood, right? So, things like that. COVID. We could talk about COVID cases, right? One of you gets it and then we got quarantines, right? Those are like exponential growth. Like all of a sudden everybody's quarantined, okay? Or one's got it, exposure like that. So that's kind of what we're doing. When you think about graphs that are exponential functions, those are things that we're talking about now in this chapter. Whoa, hey.
Sorry about that.
We're going to get to a point where we're going to, at the end of the chapter, the rest of them are just word problems. So it's like applications of all of this stuff. Okay? All right, so an exponential function, the base is a constant, and the exponent is a variable. So instead of having variables as the base and numbers as the exponents, we're going the other way. The base is a number and our exponent is a variable. They are of the form y equals a times b to the x. Sometimes that a is a 1, sometimes he's not. Okay? Let's zoom in. Okay. Number 1 there says sketch the graph of y equals 4 to the x and then state the domain and the range of the function. I'm going to grab a calculator. If you want one, you can grab one. If you don't have one, that's okay too. You can plug things in, but let's go ahead and plug this guy into our calculator. 4 to the, I'm going to use the caret, x. Okay, so when I look at the graph of this guy, notice how he's going along and then all of a sudden, whoosh, he gets real steep real fast, right? Real big real fast. So let's go look at our table. Remember when it's got that E with it, and that's kind of hard to see, I'm sorry. That means scientific notation. So that guy has 3 zeros in front of him. So he's getting smaller and smaller and smaller. So I'm going to graph ones that are nice and easy. At 0, I'm at 1. At 1, I'm at 4. And then, holy cow, I'm off my graph, right? 1, 2, 3, 4. But as I scroll up this way, all I'm doing is adding zeros. Am I ever getting negative? No, he's not ever crossing the x-axis. This guy's just getting closer and closer and closer to 0. So he's kind of like that. In fact, you can think of that x-axis just like we did with our hyperbolas, right? That x-axis is an asymptote. It's going to get closer and closer and closer to it, but it'll never touch it. All right, so then it talks about the domain and the range. Okay, so the domains, those are my x values. You're looking left to right along your graph. Do you see your graph in the negative part? Do you see your graph in the positive part? We see it both places, right? He's over here and he's up here. So our domain is all real numbers. What about my range? Greater than 0, right? We could say all positives, but we could also say y is greater than 0. Positives, there we go. So there's no number that there's no real number that I can't put into my function, right? I could put like negative 38 in there if I wanted for my x. But I'll never get anything smaller than 0 out of it. 0 or smaller. Okay, so characteristics of an exponential function. Exponential functions are continuous, meaning I can draw it without picking up my pencil. So I can draw it, there's no holes in my graph. It's not like a hyperbola where I have to pick it up and I have to draw the other side. Okay, it's continuous. I can do it in one fell swoop. I do. What cost you though? Eternal fame for me. Okay. The domain is always the set of all real numbers. The x-axis is an asymptote of the graph, meaning, like I said, it gets closer and closer and closer to it, but it never touches it. The range is the set of all positive numbers if a is greater than 0, so if a is positive, and all negative numbers if a is less than 0. I'll show you something with that in just a second. The graph contains the point 0, a. This means that a is the y-intercept. And the graphs of a times b to the x and a times 1 over b to the x are reflections across the y-axis. Okay, so let's talk about this guy for just 1 second. Let's think about all of these things with our equation up here in number 1. So in number 1, it was y equals 4 to the x. Well, we didn't have an a value, so that guy would be 1. So this guy was y equals 1 times 4 to the x. So based upon all this stuff, our a value was positive, so my range was all positives or greater than 0. Does that make sense? We also had the point, my y-intercept was the guy right here, 0, 1. You see that? Because of that guy right there. If this guy were negative, then he would drop below the graph like that. Does that make sense? So, then this guy says y equals a times 1 over b to the x are reflections across the y-axis. So think about, we'd call that exponential decay, radioactive decay, stuff like that. Okay, half-lives and all that good jazz. All right. Questions so far? Okay, there are two types of exponential functions. This one that you see right here, we call exponential growth. That's when the base is a number greater than 1. So in this case, my base was 4. So he's growing. He's getting big faster. The other one I get is called exponential decay. And that's what I just said. You get half-lives, radioactive decay. You have half of it left, half of it left, half of it left, that sort of thing. For exponential decay, the base is a number between 0 and 1. The base number is never usually negative. We would then call that a value. So you're looking for at this number right here. So it says determine whether each function represents exponential growth or decay. So y equals 0.7 to the x. Well, this guy here is my base. Yeah, it's 0.7. He's smaller than 1, so this guy is decay. Okay, look at b. Y equals 1/2 times 3 to the x. Gross. My base is 3. That's bigger than 1, so this guy is growth. Letter C is a tricky one. Don't let him fool you just because he's a fraction. What do you think, JJ?
Growth.
Growth. He's 4/3, right? It looks like it's a fraction, so it should be decay, but he's really bigger than 1. What about, and I don't think there's, oh yeah, I do. What about something, this one's not on your notes, but what if it was something like that? Y equals 3 to the negative x.
Didn't go down.
What happens with a negative exponent? Think about negative exponents. What do? They flip it, right? This guy would then become y equals 1/3 to the x. So what would that guy be? Decay. Hintity, hintity, winkity, winkity. So if you have a negative exponent, remember them makes that number move. Flips it to the denominator, so that guy would be decay. JJ.
Is there any fraction that if you flip it, it will be less than 1?
What do you mean?
4/3 after fraction. 4/3 is less than 1.
Yeah.
No, I mean like it's less than 1 before you flip it. No.
No, I don't think so. Because it has to be one or the other. It'll be bigger than 1 and then smaller than 1. Good question. It's making my brain think, though. I'm going to have to check that out. Okay. Questions on growth and decay? Okay. Number 3 says simplify each expression and use the properties of powers. OMG, rewind your brain all the way back to chapter 5. Ugh, right? So we want to use the properties of powers. Maybe we better have a refresher. We just had a little bit of a refresher here with our negative exponent. So remember, if you have, I'm trying to think, a to the negative n. That's 1 over a to the n. Remember that? That was one of our exponent rules. And then what if we had this? What do we do there? add them, right? And then what if we had this? Subtract them. Woo. I did right, legibly. And then what if we had yeah, you kind of distribute it, right? So that'd be A to the M, B to the M, all of those ones. Those look familiar. We're going to be doing that now, except for sometimes our exponents may be variables, and that's okay. Okay, so number 3 here said, simplify the expression, use the properties of powers. 5 to the root 3 divided by 5 to the root 2. Okay, well, I'm dividing. You could also write it like this. Keep the base, subtract the exponents. So even though they're numbers now, I'm still going to keep the base. So this guy is 5 to the root 3 minus root 2. Oh man, so now we've got exponent rules. We now have radical rules. Can I do anything to that guy? Can I subtract root 3 and root 2? No, the radicands aren't the same, so I'm all done.
What is that saying?
5 to the root 3 minus root 2. Okay, how about the next one? Oh, we didn't write that one on our notes. How about this one? A to the M to the N. What do I do there? Multiply. Okay, so here I have one base, power to a power, so I'm going to multiply these guys. So this guy is 6 to the root 5 times root 6. Can I multiply root 5 and root 6 together?
Yes.
Yeah, so that guy is 6 to the square root of 30. Does 30 break down?
Yes.
Let's try it. 3 and 10. 2 and 5. Does anything come out? Nope, just kidding. But we checked. Okay, questions on those? Still need to know your exponent rules. Okay. Property of equality for exponential functions. And it says it's useful for solving exponential equations. If b is a positive number other than 1, so where my base is some other number than 1, then b to the x equals b to y if and only if x equals y. That means that if I have two numbers or two equations or two expressions or whatever and they're equal to each other and they have the same base, I can ignore the bases and just work with the exponents. Well, that's pretty sweet. It also works for inequalities. So if I'm working with two expressions or an equation and I can get those two bases to be the same, well then I can ignore the basis and solve with my exponents. Okay, so turn your page.
Wait, what was the last one?
Inequalities. Okay, some of you, or those of you here in the room with me, we have the chart up on the board. If you still have your chart, you can get it out. Otherwise, we're going to need that. I'll see if I can find my binder so I can show you guys at home. I can make more copies too, so we can all have fresh ones if we don't. I found it. Okay, so based upon that last equality rule, it said if I could get these two guys to be the same, then I could ignore the bases. So if I could get the 4 and the 256 to be the same, I could ignore those bases and work with my exponents, right? Okay, now the trick is you have to go smaller. I can't make 4 bigger. I have to make 256 smaller. So I'm going to look at my chart and see if I can find a 256. 4 to the 4th, right? 4 to the 4th is 256. So I'm going to rewrite this guy instead of 256 as 4 to the 4th. Okay, my rule just said if those two were the same, then I could ignore those bases and just work with my exponents. So that means that 9n minus 2 is equal to 4. Well, that just got a whole lot easier, right? It's now an Algebra 1 problem. So I'm going to add 2. And divide by 9. 2/3. We could check that guy if we wanted. We could say 4 to the 9 times 2/3 minus 2.
Wow.
Look at us. Okay, so look at B. I have 3 to the 5x equals 9 to the 2x minus 1. Remember, you have to go smaller. So which one's bigger, 3 or 9? 9. Can I write 9 as 3 to some exponent? 3 squared. Okay, so this guy is 3 to the 5x equals 3 squared to the 2x minus 1. What happens with those guys? Multiply. Power to a power. We're still using those exponent rules. The base is the same, so I can get rid of them. So 5x is equal to 4x minus 2. Subtract the 4x, so x is equal to negative 2. Okay, now, be careful. Because in number 5 it says 5 to the 3 minus 2k is greater than 1 over 625. I said you have to go smaller, right?
Yeah, but 5 is smaller.
But 5 is technically the smaller one, right? So 625 though, how could I write 1 over 625? Gabe, what do you think?
Negative exponent.
Negative exponent. I love it. So this guy is really 625 to the negative 1, right? Could I now write 625 using my chart as a base of 5?
Yeah, 5 to the 4th.
5 to the 4th. So he'd really be 5 to the negative 4th. Okay, they have the same base. I can ignore the bases. So 3 minus 2k is greater than negative 4. I'm going to subtract a 3, so negative 2k is greater than negative 7. Uh-oh, what's happening? What do I got to remember to do? Flip your inequality. So k is now less than positive 7/2 or 3.5. Okay, questions on that first section? Okay. If you do, holler, throw them in the chat. Let's look at your worksheet. Okay, I'll admit on this one I cut and pasted. That's why the numbers are kind of crazy. So, your 1, 2, and 3, you're going to graph them. Don't forget to tell me the domain and the range. Okay? It should be pretty similar for all of them. Okay? 4, 5, and 6, you're just determining if it's growth or decay. Be careful with number 6. That's why I went over that one in your notes. I added one. 13 through 18, you're using your exponent rule. So power to a power, you multiply. If you're multiplying, you add your exponents. If you're dividing, you subtract your exponents. 19 through 24, you need to get the bases the same so you can use your chart. Okay? Questions on any of that from 10-1?